Students to come?
You don't know. I don't know. Maybe.
So there are a few things that. So I'm very glad that we have the opportunity to meet in person before the exam. The exam, as far as I know, is July 20. The format of the exam is going to be the same as in previous years. So they ask 4 questions, which should represent the material covered during the semester. As usual, the format would be similar to the problem set, the format of the problem set that we have. If you did your problem set by yourself, you should not be worried. Sometimes I take the questions from problem sets. So just that you know that. So if you somebody was not doing the problem set fully by himself, you might see that. Yeah, we'll find out some new problem sets for you guys, new questions for the exams. Hopefully, it will not be too difficult. Right, any further questions on the exam?
Can you maybe upload exams for?
Oh yeah. I'll put down the exams for myself. And use the suggested solutions. Obviously, I solve all the exams before I do the questions, so that I know if it's solvable with it. I'm given the exam. Normally, if you know the material, you can solve it.
You are
Half an
the
hour.
one who checks the exam. I mean, can you
I am
take
training the
people?
exams. The rule is that the tutor actually is grading the homework and I'm grading it. Okay, so this is the last lecture. We're doing cosmology. So we're going to first finish what I call the essentials. And then I think my impression is that it will take about 1 hour to do. And then there will be 1 more extra hour, which I asked you last time if you have any questions that you want me to address. The word few. I'm not sure, so we could talk depending how much time I have and how much my feeling is, because we might be talking a little bit about inflation, we might be talking about the cosmic microwave background, or we might be talking about the thermal structure universe. We can do all 3. Inflation requires a little bit of basics of quantum field theory, which you don't have in smart center. Maybe we can go over it. We'll see how it goes. But first thing first for the essentials. So the essentials is the Friedman-Robertson-Walker universe, FRW universe. So we have the Robertson-Walker metric, d squared plus a squared t, the r squared multiplied by 1 minus k r squared plus r squared plus sin squared theta d phi squared. And the scale factor a its evolution is determined by Friedman's equations. A dot dot of a is minus 4 pi g 3 over 3p, and a dot of a squared is 8 pi g 3 rho minus k. And show that we have for rho, for the density, we have rho matter plus a minus 3, rho radiation plus a minus 4, and rho vacuum plus a power 0. That is 3 energy contents of the universe. We went back in time and we spoke about the Big Bang. So this is T, this is A of T. We are here, 0, this is A. 0, That's when we go back in time. Good. We go back in time. So we 1 over 0. Then we reach a point in time in which a of t approaches 0. We call this a Big Bang. So all the coordinates spread together. Again, I stress again because this is a very common mistake that people are having. It does not mean that the universe was infinitely small. It could have been, and possibly I think it was, that's my opinion, infinitely small.
So just everything was
Infinitely dense, yes. And again, it's an analogy. If you take a piece of paper and shrink it, and you take a Xerox machine and copy it 50%, then 50% is much denser. If the initial paper was infinite, shrink it by 2, it's still infinite. Okay. And then we show that for the future evolutions, if it's open and closed, if it's an open and flat, future will go to infinity, open, flat. If lambda is equal to 0 and it's closed, and it will go back to 0. So closed universe is closed in space as well as time. Sorry, time as well as time. Okay. Then we define a thing which is called the kosmological redshift. So that because the scale factor multiplies all the spatial coordinates, then when we are looking at a distant object, what we're really saying are photons that are emitted from that distant object to us, right? Because we're not going to. So these coordinates. Since I have t grows in time, we are the observers. We are here. There is some extraterrestrial life that sends us photons. By the time these photons reach us, the universe has expanded. So we're going to see these photons being redshifted. The definition is that Z is lambda naught minus lambda 1 over 1. 1 minus 1. So this is not a Doppler shift. Although the calculation we did is very similar to the Doppler shift, because the objects are not moving. It's the universe that expands. Now, redshift is something which we personally, observers, do see, because we're looking at hydrogen lines, helium lines, and other lines in other galaxies, and we can identify those. And they're seen, but with the redshift. This redshift really represents a change in the scale factor from the time it was emitted to the time we then observed. Okay. This is, what we said last time, this is in addition to the gravitational redshift. Same for objects. Typically, when we look at very distant galaxies, obviously we cannot resolve individual stars, which are single from light coming from these galaxies.
בדרך כלל מה יותר משמעותי? הצלחה לאדום הכבידתית או...
When we look at different at distant galaxies, this is nearly always right. If you remember when we were talking about gravitational redshift, we saw that for most objects, except from the really compact ones such as neutron stars or black holes, this is very small. From the sun, if I remember, it was something like 10 to the minus 6 or so. 1 part in a million. Here you can get redshifts. We see distant galaxies up to redshift of 20%. It's a question of how do we measure distances. We spoke about distance measurement. We saw that there is more than one way to measure distance, which in a sense this is a very undefined question in a way, because how do we define a distance to an object in a universe that constantly expands, constantly changes? So we saw that there is more than one answer to this question. And we said that one answer is the luminosity distance, dl, which is defined as L dl squared over 4 pi f. So L is the total luminosity of the object, how much energy it emits per unit time. So the units will be hertz per second. And F is the flux. So the flux is the only thing which you have to measure. So how much energy you see per unit time, per unit area. So it is something like percentage per square percent. And the idea is, as we demonstrated last time, the idea is that if we had a universe that was flat and not moving, we had a source of photons, we're located distance r from it, dl. Right? Then this is what we this is the flat. So it's an isotropic emitter. That's the flat that we would see. So this is what the telescope can measure. But I said it can be our eyes as well. Okay. And then we saw that if we want to connect that to measurable quantities, we end up that dl A naught r times 1%. So it was one way of measuring distances. I told that there is more than one way. I introduced two. The second was the angular distance. So the angular distance is if we can measure the angle to a distant object. So for example, we are here, we're looking at the galaxy. The galaxy is sufficiently nearby so we can see photons emitted from the side, from the two galaxies, from the two edges of the galaxy, so we have an angle, right? And we can measure the angular distance. And we show that the A is A naught r minus 1. It's the angular distance to this object. Now, by far, let's think about that today. By far, the most useful place where we use angular distances over luminosity distances, maybe you know, is the cosmic microwave. Okay, we'll look at the cosmic microwave, and I'll speak a little bit of that too. And so was the distance measurement. And then by using h naught, h naught is a naught over a at t naught, and q naught, which is a naught over a naught squared t naught, we managed to connect the L. Of course, we don't measure directly R. There is no way for us to know, and we don't measure directly A. But we managed to connect the L to things which we do measure, which is Z. So we wrote down the L equal h naught minus 1, z plus 1 half 1 minus q a naught v squared plus whatever the higher order terms. As I mentioned, this formula was derived first by Edwin Hubble himself, and bears his name. This is Hubble's law. So that connects the luminosity distance to the redshift. And I told you last time that Hubble had two discoveries that completely changed the way people think, people understand the universe. The first one was, he was the first to identify another galaxy. Until his time, people thought there is only the stars were just evenly distributed in the universe, and they didn't realize that how many galaxies. And he managed to prove, so he identified the Andromeda galaxy, and he managed to prove that stars in the Andromeda galaxy are way, several orders of magnitude more further away from us than stars in our own galaxy. And then he also managed to measure, using Hubble's law, measure the distance and the redshift to a group of nearby galaxies, and wrote down Hubble's law, which is essentially proof that the universe is expanding. Now, Hubble never got a Nobel Prize because at that time of that work, astronomy was not considered to be part of physics. Now they actually changed that after World War II, and he was about to get one, and he just died a few months before, and they already decided on him, but they never announced him or something. That's a sad story. I think this is as far as we went to last time. Any further questions? Okay, so I told you there are a few more things that are essential. So let's go first over these essentials. Okay, so the next thing that I want to do is the evolution of the scale factor. Should I erase? Should I erase that? Evolution of the scale factor. So in principle, well, we don't know the absolute value of A. There's nothing that prevents us from solving Friedman's equations to get the evolution of the scale factor. Of course, the evolution depends on the values of K, whether the universe is open, flat, or closed. If we want to solve that, and then rho. Okay, so if we are solve these equations, then we have, as we showed last time, the previous lectures, we had P is equal to omega rho, and we get rho 3/3 meters, right? So rho is goes A to the power -3. And then we got that for matter rho m goes A -3, omega is equal to 0 for radiation, omega is 1/3, so radiation goes -4, and for cosmological constant, omega is -1, so rho lambda goes A to the power 0. So this really means that rho m of t is rho m t0 times t0 over A over 3, right? Which is critical times omega meter times 1 plus z. Okay. 1 plus z later. Omega meter matter is raw matter today. Raw critical is 3. That's word
So,
Yeah.
I think I lost you. How will you derive this?
Which one?
Like, what you try to say to them?
This just follows directly from here. This just follows directly from here. The rest was derived previous lecture. For radiation, it's raw radiation, 0 times A not over A power 4. Yeah. So this is from C, radiation times 1 plus Z 4. And for the vacuum, this is not changing. Go vacuum. Vacuum. So now we have to rely on observations. But you pretty much see what happens. So observations tell us that omega total is omega total is omega is nearly exactly equal to unity. Omega matter, including dark matter, is about 0.3. Omega radiation is just forget that number 8.2 times 10 to the minus 1. So today, forget for a second about vacuum energy. We have much more matter in terms of energy content than radiation. But if we go back in time, high redshift means more back in time. So obviously this was not always the case. There was a period in time that the radiation, energy density of the radiation was greater than the energy density of matter. Pretty straightforward to calculate what it is. Now this time has a name, this is called equilibration. So we should say right now. Today omega matter is much greater than omega radiation. But at T equal T equilibration, they were equal. And before that, the universe was dominated by radiation. So the time in which they're equal is called equilibration, and of course the A is called A equilibration, and redshift is called Z equilibration. Straightforward. So 1 plus Z equilibration is A naught over A equilibration, which is equal to what? What's the equilibration? I'm surprised by the this.
Well, the radiation.
What?
Well,
What? When was the equilibration?
it's equal to what?
What redshift was the equilibration? redshift today? What is the redshift today?
A0 over A1 minus 1.
Which is what? What is the redshift today? What is A today? So what is the redshift today?
Minus 1. It's 0.
0.
Yeah.
Today, redshift is equal to 0. Right? I go back to the past. So today, let's say this is the row. So what is the row matter today? So let's divide it. This is O over rho C.
Ah. So 0 over
So we have omega meter. How does it evolve? If I go for this is Z increases, right? So this is Z goes up. How does it evolve? Row meter. How does it evolve?
plus 3 to the power 3.
Plus Z to the power 3, right? So it will go something like that. And so this is row meter. What about row radiation?
1 plus Z to the power 3.
So it's much lower, right? Because now it's only 8.2 times 10 minus 5, but it grows faster. This goes as 1 plus Z cube, and this goes as 1 plus Z power 4. Right? So it will reach here the equilibration. This is Z equilibration. So what is the value?
Or you need to put a rho radiation divided by rho meter.
Yeah, what do I get?
That Z equal rho radiation divided by rho meter minus 1.
Nice. Omega meter over omega radiation. It's right over here. Since I measured today omega meter omega radiation, and I can tell what redshift, just need to divide the number 0.3 divided by 8.2 times 10 minus 5, 10 minus 4. Right? I'm surprised that we can say that. This is about 3.6 times 10 minus 3,000. Right? So, at redshifts, which are less than 3,600, universe is matter dominated. At redshifts even before that, universe is radiation dominated. Okay. In fact, today, this is not exactly because now the mega lambda, right, the dark energies, today they starts getting vacuum dominated.
What is the estimated time that this happened?
Okay. What?
What is the estimated time that this happened? Like, how much time ago?
It's coming. That's what we're doing now. So, how is the temperature of the radiation grows? And with A.
Stefan Boltzmann.
Stefan Boltzmann's very good.
Sigma 3 to the
So if we go to Stefan Boltzmann's law. So if we have, let's see, okay, now let's put the redshift. Z minus 1 is negative. So when I say radiation, the main source of radiation is the cosmic microwave background. Of course, there is radiation from stars, but in terms of energy density, this is much less than what you have in the CMB. Now, you're right. Now, Stefan Boltzmann's law, we have T, rho radiation, right? T to the 4 goes as rho radiation. So, T, CMB. We just call it T. Right? To the 4 is T, CMB. Which is rho radiation, which goes as 1 plus Z to the 4.
that means that T goes as 1 plus Z. And 1 plus Z, that is just means it goes as Z plus 1. So 1 plus Z is just goes as 1 over n. So what is the temperature of the universe today? 2.7. So to equilibration, the temperature of the universe at equilibration is its temperature today. Remember, in cosmology, everything which is 0 is today. Times 1 plus Z equilibration. So this is 2.7 degrees Kelvin times 3.6 times 10 to the 3. So we're talking about 10 to the 4 degrees Kelvin, or which is 0.9 electron volt. Okay, so the universe was much hotter than it is today. Right. Now, just erase the Friedman equations. We write back Friedman equation. A dot over A squared is 8 by G over 3 rho minus K over A squared. So of course I need to know what is K, and I need to actually, for rho I need to take all possibilities, right?
Okay.
Combine. But now I can approximate. So first I can set K equal to 0. So for K equal to 0, you can simply ignore that. I don't know if this is true or not, for simplification of the calculation. And then I can say that matter-dominated universe, I can ignore rho radiation and rho vacuum, so I can simply look at the rho matter. And since rho matter goes as a to the power minus 3, I have here a to the power minus 3, right? And this is easily solvable. So for matter-dominated universe, the solution to this equation is simply A of t is 9 over 4 8 pi G over 3 omega matter rho C A naught cube on the third T to the power 2/3. And for radiation dominated, of course this goes as a to the minus 4. So A of t is 4 times 8 pi G over 3 rho radiation, omega radiation rho C, A naught to the 4 power 1/4 times T to the power 1. It's pretty straightforward, just plug it in here. Finally, so if you are looking, if we are looking at the evolution of the scale factor, so if I'm looking at t, and this is A of t, this will go to T equilibration. Z is equal to 0. So the equilibration is 3.6 1600. Then before that, the universe was radiation dominated. So the scale factor A of t roughly grows as T to the power 1/2.
after that, became matter dominated, so it grew as t to the power 2/3. Slightly more pronounced, so it slightly started to grow faster. This is the evolution of the scale factor. Now, what about the vacuum-dominated universe? So rho lambda over pi. So again, if I put here a constant, a dot over A is a constant. Now actually it's easier to solve even for every value of k. And we'll find out universe. If t goes as, well, if its k is equal to 0, we'll solve it right away. If this is constant, what's the answer? A dot over A is constant? The exponent. So this should be an if k is equal to 0, it's an exponent of plus minus lambda 3 to the power 1 half t. This is k equal to 0. For k equal to minus 1, this will be the sign hyperbolicus of lambda 3 1 half t. And if k is equal to plus 1, it's a cosine. Yeah, I think so. So this is called a de Sitter spectrum. That's when lambda is greater than 0. Lambda is smaller than 0, it's anti-de Sitter. Okay. So really, the universe should start expanding as exponential. How we see the universe today. This, by the way, we'll go back to that. Right? You've seen, I guess you've seen this picture before. So you see, I don't know if you can see it, right? This is why it looks like, right? This is the inflation part which we may talk about later on today. This is the, actually it's very difficult now, that's it. Radiation dominated would be very close by here, and then it goes as 1/3, and it just opens up. 2/3, right? And then it opens up. This is the scale factor evolution. Okay, questions about it? Questions about that? No. Okay.
Just about a note that you wrote in the paper. All this solution represent in fact the same space-time, just in different coordinates. Can you explain it?
What's the question? This is it. The same space-time is called the de Sitter space, which is the same for lambda. If lambda is smaller than 0, you have a different solution, which is anti-de Sitter. Okay. So the next part, which is essential, now it's I can play the game of deciding which part I should stress further and which less, is observational. So let's talk a little bit about observations. So, as I stressed telling you in this course, essentially we're talking about physics here. And we can build whatever theory we want and draw whatever conclusions we want from the theory. But any theory is it's just a theory, and it is accepted only as long as we have observational proofs. And it turns out we have 5 independent observational proofs for this correctness of this big theory. So let's discuss them. Observational. So some you may know. Initial evidence. So what are the evidence for the correctness of all this great story that I tell?
Cosmic background radiation.
Yeah, this is the second one.
2.7 Kelvin.
CFP.
What was the first one?
Redshift.
Hubble's law. Hubble's law. Right. Universe expands. Why would it expand? I remind you that in Einstein's time, people didn't believe that the universe expands. They just believed that the universe is there. Whoever was mistaken. But Hubble was the first to show that it's expanding.
Did Hubble believe that the universe expanded in a way that all of the galaxies are on the same places, but the coordinates between them expanded?
I don't know what Hubble believed in, so it's not about belief. This is what we see.
Yeah, I mean, he saw that, and there are 2 ways how you can interpret it. The first one is that galaxies are really going different sizes and distances between them increasing. Right, and the second way, as you described earlier, is that galaxies they're not actually moving, but coordinates between them they are expanding.
The galaxies are not. Yeah, the galaxies are not moving. I mean, if the galaxies themselves were moving, you would not get Hubble's law, because you have galaxies that would be moving in different directions. And what we say, if you are here, right, then Hubble's law basically tells us that all the galaxies are receding away from us. There is no, if they were just randomly moving, then some galaxies would go towards us, right? But no, they are all of them are all receding away from us. I mean, galaxies do move. I mean, Andromeda is getting closer to us, but of course much less. And the further away a galaxy is, the fastest it goes away from us. If the galaxy is 2 times further away than another galaxy, then it also recedes 2 times faster. There is no way to explain that by simple motion of galaxies. Okay. So they're all moving away from us, and their velocity is proportional to the distance.
But they also can have sort of their own velocity, right?
Yeah, they do have their own velocity. Galaxies do have their own velocity. Remember, as I mentioned, the Andromeda galaxy, for example, which is the closest to us, is actually coming towards us. We will collide with Andromeda galaxy sometime in far future. Don't need to worry, we will not live until then to see it. But remember, the Robertson-Walker metric is valid only on very large scales. It is not valid on the smaller scales. Okay, so in the vicinity of the Milky Way galaxy, you cannot use the Robertson-Walker metric. Just on very far, very large scales.
By very large scales we mean billions of light years, for example.
Yeah, I mean, if the typical scale between galaxy, typical distance between galaxies is something like giga years, giga light years. So I'm talking about megaparsecs, gigaparsecs, not even megaparsecs. times to hundreds of megaparsecs, to gigaparsecs. Okay, so very far away. So Hubble's law, all the galaxies are still away from us. CMB. Okay, yeah, we're gonna speak about the CMB. I think we have time to get a few words about the CMB. And maybe I should just mention it now. So the CMB, we said when we look around, we are saying we're surrounded by radiation. It's isotropic, 2.7 degrees Kelvin. Where is it coming from?
From the past. From the past.
So that has to go.
Equilibrium.
What?
Equilibrium.
This is something which is really confusing. Equilibration was that here rho radiation is greater than rho matter, and here rho matter is greater than rho radiation. And we said at the time at equilibration, the temperature was 0.9 degrees, about 10,000 degrees Kelvin. What is the ionizing energy of hydrogen? Remember that?
13.6.
Yeah, 13.6 electron. Now, of course, the temperature goes up as we're going back in time. Right? So that means that around here, right, there could not have existed any atoms. Because once the photon temperature reached above the 13.6, actually it's less than that, but that's the second way, then the interactions between photons and the atoms were such that everything was ionized. Right? So there was no atoms. Right? So here, at this region, you'd expect to have only protons and electrons, basically, or ions and electrons. So ions and electrons. If we go even before that in time, go even backward in time, then no kernels could exist. So no nuclear kernels, right? So protons and neutrons were. If we go even before that, there were no protons, only quarks. In fact, this is one of the way. I don't think. I have things ready at that in my lecture notes, but I don't know if we should discuss about it now. We'll see that. This can actually tell us what are the elementary particles in the universe. So if we go, as to go backward in time, right, we could not have anything, anything that was bounded could not exist when the temperature was so high. Right? So here we had quarks and gluons. Here we had ions. Now it's true that it's 13.6 electron volt. But when the temperature drops down slightly below that, there still could not be any ions, any atoms, sorry, because this is thermal distribution. Thermal distribution is a Planck spectrum. So there are a sufficient number of photons at the high energy tail of the spectrum to interact with the ions and the electrons and prevent formation of the atoms. The atoms form when the universe cool enough so that the photons could not interfere anymore with them. And this is a place which is called, this is an epoch in time, which is called recombination. Okay, so it's not equilibration, it's recombination. And it occurred at a slightly smaller redshift. So this is the redshift of around 1,100. I think it's 1,100 redshift, something like that. So this is called recombination. So here we have atoms. Here there are no atoms. Okay. Now, electrons are great scatterers of photons. So photons are being scattered over. The cross section is very high. I don't know if you've ever seen that. But you won't have optical depth was very high. If you happen to be there, you wouldn't see anything. It's like driving inside a cloud. what happens in the cloud? You have photons, but they're being scattered all over, so you don't see anything. But once the universe reached a recombination, then electrons and ions form atoms, and the atoms are much less transparent, so the photons would escape. And these are the cosmic microwave photons. So they escaped, and they're still there. They're surrounding us anywhere. They're isotropic, so everywhere we look, you see them. And of course, they cool down as the universe expands. So today they reach 2.7 degrees Kelvin. They're still here. So the prediction was a great success of this model. The discovery that was a fantastic Wilson. It was 1964. Yes, so prediction was in the 1940s. This was a famous Alper Eto Gamov ABC paper that they predicted that cosmic microwave breakdown. Discovery was in 1964, and of course this is Penzance and Wilson, and then of course Frederick as well a few years later. So this is another second independent proof of the Big Bang. What's the third one? So there are 5. So one is, so these two are the most famous ones. What are we made of?
Carbon.
Atoms. Mainly carbon, not only. Well, where are these atoms made?
From stars.
From the stars. You took it in a. And what is the fuel of stars?
Hydrogen.
Hydrogen. Okay. So let's go. And where did that come from?
While star is living, it creates other elements.
Yeah. Stars creating elements are created in the stars. So when the stars end their life, and some will blow away, then they're going to see elements. But to create the elements, there was something initially that the fuel that they started. So that's called the primordial abundances of the elements. So almost the initial, before the first stars were even made, there were some elements in the universe. So this is the very light elements. So it's not only hydrogen, it's the lightest element. So it's hydrogen, helium, deuterium, heavy helium, heavy hydrogen, and lithium. And these were made right here. Right? When the atoms recombine. Now, if you know the evolution of the scale factor, right, and you can calculate what would be the ratios of the elements that are produced. I can show you that. It'll take me some time. I can show you something. So that's called the primordial abundances of light elements. Other name which you might have heard is called the Big Bang nucleosynthesis. So the idea is that everything which is more massive than lithium was created in the stars. But up to lithium, these elements were created in the Big Bang, in this recombination epoch, essentially. And by knowing the rate of the scale evolution, we can calculate the expected rates of these light elements, and we can compare them to what we see. So everything here was formed within the next 20 minutes of the Big Bang. if you're looking by mass, heading for hydrogen, primordial, it's about 2.45, and the rest are smaller, but so D of helium, primordial is 3.6, 10⁻⁵, and helium 3, for hydrogen, primordial is 1.2 × 10⁻⁵, lithium 7, hydrogen, primordial is 1.2 × 10⁻⁵. So the other thing we can measure, we can compare them because we do have a theory of how they're produced. Okay, so this is the third. Then there are 5. What will be the other 2? Fourth one is something which is very simple. It's the galaxy evolution, galactic evolution. I mean, when you're looking at a person, you can roughly tell the age of the person. If it's a baby, if it's a young adult, if it's an older one, if it's an elderly guy. But just by looking at the person, people do look differently in different stages of their life. Right? So the same is true for galaxies. Right? There are structural and morphological differences between different galaxies. There are young galaxies and there are older galaxies. Right? And when we look at distant galaxies, right, the more distant they are, obviously, what we see are younger galaxies. So we can tell. Okay, I'm going to speak about it. I just mentioned here that more distant galaxies look younger than nearby galaxies. That is related to what is called structure formation. The universe. And last bit, I think you've heard. Yeah, it's related to the cosmic microwave background.
Maybe also some sort of radiation, but
Yeah, it's a fluctuation to the cosmic microwave background. You may have heard that. Right? It's called the baryonic acoustic oscillations. BAO, baryonic acoustic oscillations. And I thought this is nice and so much that we have about half an hour, so I think we can go to that because this is nice enough, simple enough, and important enough that we talk about it. Okay, this I'm going to spend another 20 minutes discussing. Essentially, these are fluctuations in the cosmic microwave background radiation. And
it's like a thermal fluctuation or quantum fluctuation.
neither. I'm going to explain that to you. And these are related to the distribution of galaxies that we have in the universe. Since I'm going to explain that. Okay. So again, these are 5, again, as I mentioned, independent evidence for the story of the Big Bang. this can be used to eliminate alternative modes, discriminate between alternative modes. All right. Any questions except from the last one, because we're going to speak now about it.
How the third one can be proof of Big Bang?
Right.
It can be. Why the third evidence?
Primordial
Can be-
abundances?
Yes, can be proof of the Big Bang.
Otherwise, because if you're looking at the ratio in the primordial universe,
Yeah,
what
but
is starting?
we cannot.
What do we look at? Of course we can.
We can't measure what is the density of. But how?
What do you mean? You're measuring the abundances of the elements in the early universe. So you have gases, clouds of gases. Right? And you can measure how much fraction of helium you have versus hydrogen in the gas, or lithium. And this is very small. This is 10 to the minus 11 in abundance. But if you're averaging over the entire universe, the faraway universe, not what you're seeing in the stars, not in the sun, it's not relevant to us, but to the first stars, before that, gas clouds that were there in the ancient universe, that's what you see.
So you mean that we can just see the spectrum of those elements, like stars, light goes from this clouds.
Yes, there are absorption lines and emission lines, yes, from the first galaxies, first stars.
Okay, but how it proves the Big Bang?
Again, how do you produce an amount of helium-4 which is exactly 25%, close to 25% of helium? Why would it be? If you are believing this story, it's only to believe that everything is calculable, right? Then it's pretty easy. If I can tell you what is the rate in which the temperature changes, and I know what is the rate, we just calculated it, right? And I start from a very high temperature, then you can, and you know what is the rate of ionization. Then you can calculate what should be the rates of this abundance, these elements. I can do this calculation now. I have it here.
Okay, maybe if we will have time.
And now I have to select what I'm going to talk about next half an hour. I want to talk about these fluctuations in the cosmic quick record for now. And then at least I'll mention a little bit here, the history of the universe. CMB. So, okay, any further questions about that? No. Okay, so just that you get the idea of what happens here. CMB fluctuations, or it's called actually CMB anisotropy, cosmic microwave background anisotropy. So we said, when you think of it, right, the first signal that we can have from ever, right, is this cosmic microwave background. So we're going back to this picture again. Right? This is the first signal that we can have. Right? Before that, whatever happens before that, we had no way of telling because photons were coupled to the particles to the electrons here, and we didn't see them. So the first signal that we can have is this cosmic microwave background. They came out at redshift of about 1100. Right? We cannot see anything beyond.
Can you explain again?
What?
Can you explain it again?
Yes. Right here, we had no atoms, only electrons and ions, protons and neutrons. Right? If we go further before that, we didn't even have them. Right? So all the photons, we couldn't see them. Photons were just scattered all the time. Like the scattering was very high. So it was basically like driving into a cloud. If you happen to be there, you couldn't see anything. Driving inside the fog, or something. Very thick fog, which you couldn't see anything. Because the distance the photons travel were very short. Once atoms were formed,
illumination, there was nothing to scatter efficiently the photons anymore, then they just move on. So that is what we see. This is what we see. Okay. So if we are looking outside, now why don't we see them? Because 2.7 degrees is in that millimeter. So you need to have a millimeter. Where you see that, again, today you don't see that, but when I was younger, there were these televisions that use antennas. So they were not connected via cables. And then there was always noise. Right? Even if you're very good, there will always be some noise. Some white noise. Called snow. This is exactly the cosmic microwave. So if you look in the cosmic microwave background, if you look at millimeter, that's what you're going to see. Looks completely isotropic. Now, if you are looking at small fluctuations, I have a T is 2.7 degrees, 2.726 degrees Kelvin, very close to but above the absolute zero. Right. If you are now looking at small fluctuations at the level of 10 to the minus 3, so delta T over T of about 10 to the minus 3. Then you will see something. What will you see? It's something that looks like that. Why is that? That's a dipole. Why is that?
Some part is colder than other.
Yeah, you'll see that some parts is hotter than some parts are colder. Delta T over T or why is that?
That's a good question.
It's actually a very simple question.
I think that because the universe has galaxies that not uniform. So
Galaxies are uniform. And the 2.7 degrees got nothing to do with the galaxies, because this is not radiation that comes from the galaxies.
Maybe colder part is where we are living.
We are right in the center.
Oh, really?
Yeah, these maps are always very in the center. Well, that's easy.
This is, it's just like the second order polynomial Legendre plus equations.
It will plus equations. Question in physics. Why do we see now? Why do we see this small variation, delta T over T 10 minus 3? Well, where is this dipole coming from?
our measurements.
Our measurement tool is perfect. Come on. Are we static observers?
No.
What are we? We're moving through the universe, right? We're rotating, we're moving around the sun is moving around the center of the galaxy. Right? So what do we see?
Doppler.
Doppler effect. Simply a Doppler effect, right? We're going in this direction, and the photons are being Doppler boosted, so they're seen to be slightly hotter than they are when they're receiving waveforms. Okay. That's it. So this was the situation for many years.
Okay, but how people get the first picture?
Get it in the 1960s. Just take a horn, which you're sensitive to. That was the clever thing that they did. The problem was that 2.7 is very close to absolute zero, and so the thermal noise that you have in your detector is typically much larger than this. So Benzias and Wilson's clever idea was to put the detector in liquid hydrogen, liquid helium. Now, that was not enough to put it, but they were just flipping it, putting it in liquid helium, and then they went up to observe, put it again. So they were doing something for flipping. It was the clever method of cooling the detector such that they will not be affected by the thermal noise of the detector itself. Right? Because this is very, very small. It's very close to zero, so you have to have your detector to have thermal noise in the detector has to be very, very small. They were the first to have a detector which was so sensitive. Okay.
And I just looked upside. Then they put it in some building in Princeton, and they just look upside. And everywhere they look, they saw this. That's very easy technique, right? So when things got better, you can see that after that delta T over T that minus 3, you could identify there are some fluctuations. But they are associated with our motion.
So, but to do it, he needs more better detectors, right? Than
yes,
60s,
less,
right?
yes, with less thermal noise.
Mm-hmm.
Yeah, you cool them better to make sure to reduce the noise, of course. Okay. The next jump comes in the 1990s. Now we're going about 30 something years ago, and then they detected this map. Okay, so this is already at the level of 10 to the minus 5-ish. So delta T is 7 times 10 to the minus 5. Then when you start to see fluctuations, and then you're seeing essentially this picture. So again, this is the universe. We are here in the center, and orange regions are regions which are slightly hotter, still thermal, but at slightly hotter temperature, and colder regions are regions which are slightly colder. And it looks like a random map, but it's not a random. Right? So after you take away this dipole, so you compensate for the motion of the Earth, this is what you're seeing. Okay. Now, what do you see? What do you do with that? Delta T over T is just T minus average temperature divided by the average temperature, T of M, location. What do you do with that when you have such a map? So if it was a one dimension, what would we do? What do we want? What to analyze? What to extract some physical information?
In the gradient.
What do you do with that?
It was one dimension. So
It was
they
dimension.
connect it for each point.
What do we do?
They connect it for each point.
Let's say that just cut it down. Just to as a method to 10. Okay, you do it for, I'll explain, you could say you do a Fourier transform of some kind. Now I'm pretty sure that you've seen that in your client, but I'm not sure. Do you know what is the YLM expansion?
Yes.
Yes. Where did you see that?
Mathematics and physics.
Mathematics for physics.
I did so.
What?
I did so.
You didn't see that?
משפט הסכימה.
Ah.
Did you see that? It's the harmonic, spherical harmonic expansion.
Ah, yeah.
So that's the YLM. So what you do, basically, you expand it in a spherical harmonic. So you do delta T over T, and you sum for LMM, ALM times YLM, that time. So it's just a way of modeling this on the sphere.
Yeah. Inside there are.
So you do the expansion. And then you're looking at the expectation value of the coefficients. Okay. You're doing the expectation values of the coefficients. CLM is ALM absolute value squared average. And what typically people are showing is not the CLM, but they show the L plus 1 C. For it gives you more clear physical information. And what you see, I have it on this one. I didn't put it in the video. What you see is something that looks like that. So you look at the function of the multiple moments L, and you do a power spectrum. So B of this CNM. And you have the multiple moments, which essentially represents the angular resolution. This will be like
10, 50,000, 2,500. This would correspond to some angular resolution. So 50 would be about 1 degree on the sky. This would be something like 0.1 degree on the sky. What you'd see is something that looks roughly like that. So essentially what you do, you're looking for correlations. That. Looking for various correlations in there. And you find that when you go to 1 degree, so this corresponds to L of about 50, there is a roughly really strong correlation. When you go to higher or lower, you get much less correlation. This is not a mistake. It's not some the angle theta is roughly pi over L. If you remember what we talked about last time, right? The angle at the last scattering surface, right? So the combination, you get a theta at lambda moving is lambda divided by dA at z recombination times 1 plus z recombination. Lambda is the scale. So where do these peaks come from? Why do you see these correlations on this scale? And these peaks tell us a whole lot about the evolution of the universe and what it contains. Where did this peak come from?
Can I ask you a question?
Yes.
When you mentioned correlations between what?
No, you just take this delta T over T. You expand it. You do spherical harmonics.
Okay.
That tells you how much power you have in spherical harmonic. So you have a lot of power. Means that there is a correlation between the region which correspond to that spherical harmonic. It's the same like as a Fourier transform, basically only doing it once. Okay, I'm assuming that you've seen this before. If you've not seen it before, then yes, there's no point of me talking about it.
So, but what's the X axis?
What?
מה זה הציר האופקי?
L. So I do it. I look at the correlations for different values. The maximum actually is around. It's not 50. It's around 200. 50 here, 200. Be around here. Which corresponds to about 1 degree. So these peaks, these are not the acoustic peaks. And what does it mean? Now it's very easy to understand what happens if you understand the whole picture that I'm drawing here. So I said here, I said no atoms. What do we have? Ions. Electrons, protons, neutrons, right? Ions. What do the ions do? They attract each other. So we have gravity that attracts each other. But then, what else do we have here? Oh, except from ions, what else do we have here? Photons. We have photons. So what do the photons do? Yeah, they push them backward. Right? So if the ions try to get pulled in, photons push them back. So it's pretty much, it's very analog to talking about two masses on a string. The masses pull each other, right? So you have some sort of a gravitational potential. The analogy would be that you have some sort of gravitational potential, and you have two masses. Here are the ions, and there is a spring that connects them. And the ions wants to go down, and they do manage to go down, but then the spring, which is the photon pressure, pushes them back. So what you have is fluctuations, right? Now these occur on all scales. Right? So you have regions of where they're pushing, right? But then there are regions which are emptier. Right? So if you look totally, then you see that also the mass here and the mass here. So also here and here. Now being pushed. Where we'll see that at the end, we could connect that to the distribution of galaxies in the universe. Yeah, right. Because the basic idea is that we had regions which had slightly stronger potential, well, and then of course after they decoupled, there was nothing to push them back, so they would just continue on, and they would correspond to the structures, but one step at a time. So we have these baryons. Right? Baryons means a heavy material that contains quarks. So basically, protons, neutrons, these are baryons, as opposed to electrons, which are light. Right? So these are getting in and out because the photons try to push them back, and they oscillate. Now, there is no scale in which this occurs. This occurs at all scales. Right? When we're here, this occurs at all scales. There is no preferred scale. Right? So we have now, and of course the oscillation period depends on the scale. The ones having on shorter scales occur faster than the ones who are longer scales. Right? Until when? Until you get the combination. So this continues on, but we have all these oscillations here. We have these oscillations going on until we reach a combination. Once we reach a combination, the photons escape. And they are no longer capable of stopping the pushing back the ions. Okay. So then what will happen? If there was a mode, it just happens to be at the minimum of the oscillation, when this recombination happened, it will create a galaxy. It will create a galaxy, but this also will create the strongest fluctuations that we see in the cosmic microwave background. So this one corresponds to exactly that mode that happened to be in the minimum at the time of recombination.
I mean, if I will repeat this experiment, do it all over again, it will look completely different.
No. Because that depends, it will look exactly the same for the same universe. It will look exactly the same. In fact, and the second one, before the second one. And when you have this deep here, it corresponds to the deep here. Now it can actually tell us much more than that. Because, for example, right, we said we have matter, regular matter that we see, but there is also dark matter. Right? Now dark matter is not affected by these interactions with the photons. That's what defines the dark matter. It is affected gravitationally, though, by the rest of the matter. Right? So this would affect what? The height of this peak relative to the other peaks. Right? So by measuring the height of this peak relative to the other peaks, we can actually get an independent measurement of the amount of dark matter that there is. from the location of this, we can also tell. Of course, this will also depend on how much matter there is, omega matter or matter radiation, everything. But if you do different, I have it somewhere. It's too small to see. It's not part of this course normally. But you can see that if you're changing the values of the omegas, this will change both the location of the peaks, and it will also change the relative heights of these peaks. So in fact, by looking at the cosmic microwave background, so this is the Orionic acoustic oscillation. So just by analyzing, now it's true we have only one snapshot of the universe. That's all. But it turns out that the amount of information we get on the cosmological parameters from that are completely consistent with what we measure in today's galaxies. So that's what I mean by this independent measure. And of course, this is the first measurement that we have. Cool. So these are the Orionic acoustic oscillations. Now, how have we started? Oh, pretty much running out of time. One more thing I'll do, just sort of summarize to you a little bit about the thermal history of the universe. This is the Orionic acoustic oscillations. A little bit about thermal history of the universe. I'll just summarize to you without going into the math, because there's quite heavy math. Okay, what is the earliest epoch that we can think of having sample knowledge about? Yeah. I mean, I want to go now back in time. How far back can I go and still say something which I believe physically is sensible?
1,120.
No. What? I mean, of course, I don't have any data, direct data, from what happens here. This is the first light that I can see comes from here. That is true. But I can still develop a theory for what happens here, and that will be imprinted on the cosmic microwave background, as I just showed.
Yeah, but theory means nothing without.
No, but theory, no. But as I said, theory, essentially the theory gives me predictions, and the prediction is something that I measure. So I'm not throwing away the theory. So I'm asking you, obviously, what we said in this course is full theories, right? Essentially, this theory has observational consequences. So what is the earliest that physics can say something?
Maybe Planck scale.
Exactly. So this is the Planck scale, right? So the energies as we go, so the temperature goes up as we go back, right? So the temperature goes up as we're going back in time. So, but the maximum temperature that can go high and you can still believe that something is meaningful is called the Planck scale. So M Planck, H bar C over G to the power 1/2. It's around 10 to the 19 giga electron volt. And the time, Planck is H bar over M Planck C squared. So that's about 10 to the minus 43 seconds. Anything that happens before that is beyond physics we understand. I think we understand. I would mention, because I was asked about the inflation, right? So the inflation is the region here, very early times. To fully understand it, we need to go through quantum field theory, which we don't do. But the basic, I will just mention that the basic questions it's about there to solve are two questions, which we went through. One is why the universe is so close to flat. It's easy to see that there is a problem there, because if you write down Friedman's equation, A dot over A squared is 8 pi G over 3 rho minus K over A squared. And we say that rho goes as A to the minus 4. write this as omega minus 1 k over a squared and h squared. I'll see that when a goes down, this is actually not an attractor. It should take me away from my unit. So it's not clear why I should get unity. So that's one problem. Second problem is essentially that. How come the universe looks so isotropic in all directions? Although photons from here never had time to communicate with photons from here. So why are the conditions such that they are all the same? Inflation is supposed to solve. There are other problems there, but that this inflation is supposed to solve, I didn't get into. Inflation is supposed to solve these problems by saying essentially that there was a period in time in which a dot dot was greater than 0. This is inflation. Why is that? Because they believe that there's no knowledge, but they say that there must have been a field that produced it. To understand that, we need to go to quantum field theory. Another thing is that when this field, this has to be limited in time. It could last forever. You have to stop at a certain point. So you have to have something that causes a dot dot to be greater than 0, and then some of this. So I won't go into that right now. Right. So this is the Planck scale. Energy was so high that beyond that, no laws of physics are not. This is one. After that, here, we had a very hot universe. It was so hot that it only contained elementary particles, which is quarks and gauge bosons. This is, for example, the Higgs level. And then, okay, then it goes back. Now I have to speak about particle physics. Get into that. So there was a spontaneous symmetry breaking, which eventually caused the formation of the particles. It's called the good phase. So the good phase. And that happens at temperature from 10 to the 16 GeV, or 10 to the minus 38 seconds. And then there was the electroweak phase. That's where electrons got their masses. So electroweak phase. That happens much later, at T about 300 GeV, or 10 to the minus 8 seconds. The baryons were formed, baryon formation, that occurs at around temperature of 100 to 300 MeV. That's around 10 to the minus 5 seconds from the Big Bang. And the nucleosynthesis, so this is the formation of the nucleus, Big Bang nucleosynthesis, BBN. That was when temperature further went down to 0.1 to 10 MeV, which is between 10 minus 2 to 100 seconds. This is where the elements, first elements were formed: hydrogen, helium, etc. Photons left equilibrium, so photon number became conserved at around 1 GeV. That's about 5 seconds. acceleration, t, well, 3 electron volts, about 10 to the 12 seconds. That's raw matter. Raw radiation. And at around 0.1 electron volt, which is 10 to the 13 seconds, which is about 400,000 years. This is the combination. Just to complete the picture, so after a combination, photons, you could see the cosmic microwave background. Matter kept on falling into the gravitational potentials until eventually the first stars were formed. First galaxies were about 10 to the 9 years. Before that, that's what you see back here. There is a region where there was nothing really that emitted light. So in cosmology, this is called the Dark Ages. So from the time we had the cosmic microwave background until the first stars were formed. It's 1980. First stars and the first galaxies. Around 400 million years. All right. So I think this pretty much concludes what I wanted to say about the general relativity. I'm basically here during the summer. Don't have any travel plans. The exam, as I mentioned, is in about 2.5 weeks, or 3 weeks. It's not written yet. I have to write it. Coming days, I'll write it. If you have any questions, come and ask. I hope you enjoyed. And wish you good luck in your studies.
Thank you. Thank you very much. Thank you very much.
Will you download, upload the exams from the last year on
Yeah,
the
he said he will. So I said we will.
אסף, שאלה בנוגע לשיעורי בית. כל השיעורי בית נלקחים בחישוב הציון?
What I said in the first lecture of this semester, I gave you all the rules. Everything is pretty set there. If you're not sure, it's written clearly in the courseware page. Did not change anything. All right. Good luck, guys.
Thank you. Thank you very much.
Good luck with the examination period.
What is the higher redshift we measure? I mean, with our telescopes.
I'm not sure I understand the question.
Combination here is the physical threshold